Good morning to one and all. In this video, I am going to explain algebra of continuous functions and properties of continuous functions. Algebra of continuous functions. Here I am taking two continuous functions f of x and g of x. Those two functions are continuous at x equal to c. Then the functions f of x plus g of x, that is the sum of these continuous functions, and f of x minus g of x, that is subtraction of these two continuous functions, and f of x into g of x means product of these two continuous functions, and also quotient of these continuous functions are also continuous at x equal to c. In the fourth one, there is one condition, that is g of c not equal to 0. This is the algebra of continuous functions. In simple way, if two functions are continuous, then product, difference, product, quotient are also continuous functions. Next we move to properties of continuous functions. Before going to prove properties of continuous functions, we need some definitions. First one is, the function is bounded above. Observe the definition. A function f of x is said to be bounded above in the set D, but D is subset of capital R. Capital R is a real number system, so the elements of capital D are also real numbers. First condition is f of x is defined at these real numbers. That means if you substitute any one of these real number in the place of x in f of x, we need finite value. Then we say that f of x is defined in the set D subset of capital R. Second condition is, there exists a real number capital M such that f of x less than or equal to capital M. Here also x is real number which belongs to capital D. That means D contains some real numbers. At these real numbers, the value of f is always less than or equal to capital M. Whenever these two conditions are satisfied by f of x, then we say that f of x is bounded above. Next we move on to bounded below definition. Here also we are taking a function f of x. This function is said to be bounded below in the set capital D subset of R if f of x is defined in the set capital D subset of R, and also there exists a real number small m such that f of x is greater than or equal to m for all x belongs to D. So all of you observe, this is a real number system. This is subset of real number system. So the numbers of the elements of D are real numbers. At these real numbers, the function is defined. This is the first condition. Second condition is, if you find the value of f at these real numbers, it must be greater than or equal to m. This is the second condition. Whenever these two conditions are true, then we say that f of x is bounded below. Observe, bounded above means f of x is less than or equal to m Bounded up below means f of x is greater than or equal to m. Once you change the places here, then less than or equal to greater than or equal to becomes less than or equal to, but f of x is again less than or equal to capital M. That means whenever f of x satisfies this condition, then we say that f of x is bounded. So observe once again, a function which is bounded if it is both bounded above and bounded below. The combination of these two inequalities is this one. That's why we can easily say that f of x is said to be bounded if it is both bounded above and bounded below. With the help of these definitions, you can get an idea about the concept bounded. These two are the examples of bounded functions. Here we are taking f of x as sin x. This is bounded because we have small m as minus 1, capital M as 1. Therefore, this is a bounded function. And also the second example is f of x equal to 2x plus 3. This function is also an example for bounded function. Now we are going to prove theorem 1. Theorem 1, the statement is as follows. Every function defined and continuous on a closed interval is bounded. So, if a function, the data is a function f of x which is defined in a closed interval a comma b and also this is continuous. Now we want to prove that this continuous function is bounded. So, it is easy, statement is very easy. Observe, f of x is a defined on closed interval. This f of x is continuous. Now we want to prove that this continuous function is bounded. So, the statement in symbolic way, if f of x is a function which is continuous on closed interval a comma b, then there exists a real number capital M such that modulus of f of x minus m for all x belongs to closed interval a comma b. This condition is same as bounded condition only. Observe, whenever like this we can write negative of m less than or equal to f of x less than or equal to capital M. So, here take these two, then we are going to get f of x is greater than or equal to minus m. Here minus m is real number because integers are also real numbers only. So, we have bounded above definition. If we consider this one, then f of x is less than or equal to m. That means bounded below. Therefore, we have bounded above concept and bounded below concept. Therefore, this is same as the condition of boundedness. Next proof. Suppose f is not bounded in closed interval a comma b. Observe what we wanted to prove. We wanted to prove f is bounded. But what we are considering, f is not bounded. That means at the end we are going to get contradiction. Why means because our assumption is wrong. So our assumption is wrong means what is the correct one? The correct one is f is bounded in closed interval a comma b. So once again, here we want to prove f is bounded, but we are considering f is not bounded. At the end we get contradiction. Why means because of our assumption. That's why our assumption is wrong. So what is the correct one? The correct one is f is bounded in closed interval a comma b. That means when we consider a function which is defined on closed interval a comma b and also continuous, then it is bounded. Every continuous function defined on the closed interval is bounded. So here we are taking f is not bounded. So observe, this is closed interval a comma b. Closed interval means end points are also included. Now I am going to divide this closed interval into two equal intervals. Two equal interval means exactly middle. I am considering a point C. So first interval is closed interval a comma c. Second interval is closed interval c comma b, where c is the midpoint of this interval. That's why c equal to a plus b by 2. Then by our assumption, it follows that f is not bounded in at least one of these intervals. Here we have closed interval a comma b, closed interval c comma b. But we are taking f is not bounded in closed interval a comma b. That's why f is not bounded in at least one of these intervals. Now we want to choose the interval in which f is not bounded. If we choose this interval, in this interval f is not bounded, observe here f is not bounded. Here f is bounded. So wherever f is bounded, we are leaving that interval. So we consider the closed interval a comma c. Now we rename this closed interval as closed interval a1 b1. So this closed interval now a1 b1. So a1 value equal to a, b1 value less than b. Here we are observing 3 points. In these 3 points they are saying a less than or equal to a1. Here we have a equal to a1. If less than is true, then equal false. If equal true, less than false. In this case, a equal to a1, less than or equal. Here, b1 is less than or equal to b. Here also, if less than is true, equal will false. If equal is true, less than will false. Now observe, b1 is less than b. That's why equal to is false. Less than or equal means anyone. If one is true, another one is false. Second point is the difference of b1 minus a1 is equal to b minus a by 2. To explain this point, I want to take values for a and b. If a equal to 6, b equal to 10. C is exactly midpoint of a and b. So C equal to a plus b by 2. So 6 plus 10 by 2. So 16 by 2. That means 8. So the value of C is 8. Now the value of A1 is 6. The value of B1 is 8 because A equal to A1, C equal to B1. Now calculate B1 minus A1, that is 8 minus 6 is 2, and also calculate B minus A, that is 10 minus 6, 4. 4 by 2 is 2. So 2 equal to 2. So second condition is also we are taken granted. Now third condition is f is not bounded in this interval. I think you can follow these concepts. Now we divide the closed interval what we have a1 b1 again into two equal parts. Okay. Then we are going to get C1. C1 is A1 plus B1 by 2. First interval is A1 C1. Second interval is C1 B1. In this closed interval A1 B1, F is not bounded. That's why F is not bounded here. If F is not bounded here, I am only considering here F is not bounded in this interval, then F is bounded in this interval. So we are not considering the interval which is in which F is bounded. So here we have F is not bounded. So again we are going to rename this closed interval A1 C1 as A2 B2. That means in this closed interval F is not bounded. And also we can observe certain points regarding this closed interval A2 B2. So observe. First one is A1 less than or equal to A2. I already told less than true means equal false, equal true means less than false. That's why in this case we have A1 equal to A2. B2 is less than B1. So first one is okay. Second one, this one also we can easily prove by taking some closed interval. So B2 minus A1 is B1 minus A1 by 2. But we already know that B1 minus A1 value. So this can be written as 1 by 2 into B1 minus A1. So this is equal to 1 by 2 into B minus A by 2. 2 into 2 is 2 square. So second one is also grantedly taken. In third one is, in this interval F is not bounded. So I think you understand these points. Again we are going to divide this interval into two equal parts. Like that, we are going to divide the interval in which f is not bounded. Then we get nested of intervals. That means one interval contains another interval. Another interval contains another intervals. These are the intervals. First one is closed interval a comma b. In this interval, a1, b1 is existing. In this interval, a2, b2 is existing. Like that, we are going to get nest of intervals. These nest of intervals, so observe, here the second point is b2 minus a2, value is b minus a by 2 square. That means if we are going to divide closed interval 2 times, then we are going to get 2 square. Similarly for n times, we are going to get 2 power n. Here f is not bounded in closed interval a to b2. Therefore, f is not bounded in closed interval an bn. Here n is 1. Then we are going to get first case. If n equal to 2, then we are going to get second case. Similarly, for the remaining intervals. So, this is the generalization of above two concepts. So, we can easily say that from this line, sequence an is monotonically increasing sequence. And also we know that every monotonically increasing sequence is bounded above. Therefore, flower bracket an, that is the sequence an is bounded above. Hence, the sequence an tends to a limit as n tends to infinity. That means, limit n tends to infinity, an must have a finite and unique value. But, limit n tends to infinity, bn minus an. That means, we are taking limit for this second point, both sides. Limit n tends to infinity, bn minus an is equal to limit n tends to infinity, b minus a by 2 power n. If I substitute infinity in the place of n, then we are going to get 2 power infinity. But 2 power infinity is infinity. Anything by infinity is 0. That means this limit value is 0. Whenever limit of difference of two real numbers is equal to 0, then those two limits must be equal. That's why I am going to take limit n tends to an equal to x naught and limit n tends to infinity bn is also x naught. X naught is also a point belongs to closed interval a comma b. So, whenever this condition is true, then we can say that, observe here, limit n tends to infinity an is x naught, limit n tends to infinity bn equal to x naught. X naught minus x naught is 0. So, it is possible to consider like this. Now, in the statement, what we have, f is continuous on closed interval a comma b. While explaining the definition of continuity of a function on interval, I explained one concept, that is, a function is continuous in the closed interval a comma b means the function is continuous at each and every point of this interval. Now we consider x naught is a point on closed interval a comma b. That means f is continuous on closed interval a comma b means f is continuous particularly at x naught. So, by using the definition of continuity, we can write for every given number epsilon greater than 0, there exists delta greater than 0 such that modulus of f of x minus f of x naught less than epsilon for mod x minus x naught is less than delta. Why I am taking here x naught? Because the function is continuous at x naught. That's why I am taking x naught there. Next step is, I think you know this step, even though I will explain once again. Whenever we have this type of condition, we can write minus epsilon less than f of x minus f of x naught less than epsilon. Take this negative quantity this side, then f of x naught minus epsilon less than f of x less than f of x naught plus epsilon. So the same step we are getting here. Similarly, from this one we can get this one. Observe, here we have one real number. Here also we have one real number. That means the value of f of x lies between two real numbers. Then we can easily say that f is bounded in neighborhood of x naught. This is called neighborhood of x naught. This point is x naught minus delta. This point is x naught plus delta. Already we have taken these two values, like limit x tends to infinity an equal to x naught, limit n tends to infinity bn is x naught. Whenever we take like this an bn compulsory lies in this neighborhood. So this is an, this is bn. So f is bounded in closed interval an bn. Y means here we have f is bounded in open interval. This closed interval is subset of this interval. That's why f is bounded in open interval means f is bounded in closed interval, because the points of a and bn are the points of open interval x naught minus delta comma x naught plus delta. In simple, f is bounded in this open interval. This is subset of this open interval. That's why f is bounded in this closed interval. But this is contradiction to our third concept. Here what we write, f is not bounded, but what we get, f is bounded. That's why contradicts to the result 3. So if this is not possible means, then we can say that our assumption is wrong. Then what is the correct one? F is bounded in closed interval is correct. From this, we can easily say that a function which is defined on closed interval is bounded. So, theorem 1 proof is completed. Now, we are going to check a function which is defined on open interval is bounded or not. But it is need not be bounded. Depending on the interval, a continuous function defined on open interval is bounded. But in some cases it is bounded, in some cases it is not bounded, depending on the function and interval. For example, here we have f of x equal to 1 by x. This function is defined on open interval 0, 1. This function is continuous in open interval 0, 1, but it is not bounded in open interval 0, 1. We can easily say that every function defined on closed interval is bounded, but f is continuous function. The same f of x, if it is defined on open interval, it is need not be bounded in that interval.